the corresponding NSECs.
Well, and you're required to change your key, too. Because, well, let's say I start out with A and C, so now my server is returning back something that says, okay, there's an A and there's a C, and I request B, there's no B. Well, later I add a B. Well, I've already returned that packet. Someone could replay that and deny service to B, right?
Yes, somebody could replay that. So there is, and in fact, we'll come to some of this issue later, is one thing DNSSEC chose not to do is have either revocation or essentially support a very much real-time update. What I'm bound by is the lifetime of this signature. And if this signature is for 2 years, then I certainly can withdraw it from my zone. That's not going to stop the attack. Right? For the next 2 years, anytime somebody asks for dub-dub, the attacker can replay this old answer and say, sorry, it doesn't exist. And I'm vulnerable exactly for that time. So that's bad, right? But why is that not such a big deal for DNS?
Short lease times.
Yeah, we can put in short lease times. I certainly don't have to change keys. I just have to resign, right? There's no changing the key. There's just keeping a short lifetime on this guy and re-signing him. And DNS was never designed to be a real-time system. In the current DNS, there's already a TTL in there. The zone file gets transferred from the master server to the secondary server. You may query any of those servers. You may hold it in your cache. So if you were hoping you're going to add dub Purdue EDU and it's going to instantaneously appear in the DNS, you were already out of luck. I may be making it worse by putting a longer signature lifetime on here. But I'm certainly not introducing a new problem. And depending on how frequently I'm willing to re-sign the zone, I can chop this down. Ideally, the time here is the expected TTL on the record time. So for a very dynamic zone, I'm going to be doing a lot of re-signing. But that's definitely a limitation of the system. Any other problems with this kind of approach? Would you be willing to deploy this on your zone? So we can get into a sort of philosophical debate on security through obscurity. What's one immediate consequence of these NSEC records? If I want to find out everything in the Purdue DNS, and the Purdue DNS is exactly n entries long, how many queries do I need to figure it out? Exactly n queries, right? I will query for Purdue EDU. It will tell me, here's Purdue EDU. The next record is a.Purdue EDU. Now I'll ask for the NSEC record in A. I'll say, give me the A NSEC record. It'll say, the next name after A is C. The next name after C is D. And I've exactly enumerated the zone file. So now we have a debate as to, is that a bad thing? And the answer, at least in the standards community, is no, it's not. The answer in the operational community is still yet to be determined. If you go to Black Hat, the first thing they talk about in the Black Hat DNS thing is look for zones that allow zone transfers. You can get all of Purdue's host information. You can, usually from the name, probably Christina identifies her boxes with similar names and maybe has a particular pattern for patching the boxes. I do the same thing. And looking at the zone file, there's a whole host of social engineering you can derive from that. You know all the hosts, you know all the data. Now, even if you've turned off zone transfers, I've essentially turned it back on for you. On the other hand, this is public data. I mean, if the security of your system was relying on the fact that I couldn't figure out there was a machine called u.Purdue EDU, I'm not convinced you really had security in the first place. And in fact, since I know your IP address space, I can use the reverse space with more queries, but still in deterministic time, to identify basically all your machines that have an IP space within Purdue's allocated range. And I can't necessarily get the entire DNS that way, but I can get essentially the effective copy. So I've introduced essentially, I've essentially revealed your zone to the whole world. And in the standards community, we've decided, the right thing to do is to say security through obscurity is not security. So you don't get it. You wanted it, too bad. You shouldn't have had it in the first place. Whether the operational community will sign on is still in the to be determined stage. Okay, so, but that being said, it's a nice system, it's clear and all, but there is no magic crypto fairy dust. Even in DNS Sec, this system took 10 years to standardize. And let me give you a few ideas why. We started off with key management. And key management in any large-scale public key crypto system is going to be essentially a practical killer unless you can do it well. The way we started off by doing it was saying we got this great hierarchy, right? And we're going to have edu sign the Purdue key. And then we're going to put that signature in the Purdue zone. And now we've got a nice chain of trust. You can start from the root, you can walk to edu, you can get from edu to Purdue, and so on. And the only problem now occurs when you try to go and change the key for edu. Or com. So VeriSign loves this problem. VeriSign runs the com zone. Suppose I deploy this system and I need to change the key for com. Who do I need to update? All 30 million star.com zones. Right? I have to, because everybody has a signature by the key I'm about to replace. So before I can replace it, everybody better have a signature from the new key, otherwise I'm potentially going to cut them off and make them appear like a spoofed zone or worse. So now I've got a real problem changing the key. And you can imagine the VeriSign people looking at this standard and saying, our lawyers love this, right? I want to change the key Monday. Cisco comes along and says, sorry, we have some internal thing, we can't change by Monday. Amazon comes along and says, yes, I agree with the need to change the key. The actual com key might have been compromised. To preserve our e-commerce business, you better change the key. So, do you chop off Cisco or do you chop off Amazon? Both of them have a lot of lawyers. You're not going to win either way. And it's not a situation that VeriSign wants to be involved in. So we need essentially a different operational system. This system it was originally developed by the military where this made sense. You have a top-down authority. The top guy can say we're changing keys. The guy below him will do it. But in the commercial world, in a real distributed system, this doesn't make sense. So sort of the graphic of how you change the key is this. This is the coordination problem between edu and one of the children, or between com and one of the 30 million children. The first thing Purdue edu does is send its key up to the parent. The parent sends back a signature using its key P1. When I want to change to P2, the parent first has to add P2. It's got to go to its parent, get a signature from its parent saying, yes, it's okay to add P2. Then it's got to start shipping out P2 signatures to all the child zones. After they've acknowledged that's been replaced, we can actually go ahead and replace P1 with P2. Then we can actually remove the old P1 signature from the zone. And remember, all these guys have lifetimes that need to be refreshed or restored. And if we're running up against the end of a lifetime here, this entire thing can be compressed, or potentially require signing with an old key. And I'm doing this 30 million times on 30 million different sets. So the main change in the standard between 2035 and the current one that came out in February is really all in the key management. Most everything else is details. What we've done is we've just done the standard computer science trick. A layer of indirection is going to solve anything. We took the SHA-1 hash. The fact that the SHA-1 hash only saves us room. You can think of this as simply taking a copy of the child key, storing it in a different record type at the parent. We call this the delegation signer or the DS record. We take that up at edu. The DS record is stored solely at edu, is signed by the edu key. If edu needs to change keys, it simply re-signs the data at its local zone. The child zone, Purdue, needs to make sure that it has at least one key in its set that matches this DS record. Because the resolver is going to authenticate the DS record and say, I'm looking for a Purdue key that matches that DS